This video is going to walk through an example of proving a language not context-free using the pumping theorem for context-free languages. So what you'll need to remember is how we have used the pumping theorem for regular languages to prove that languages are not regular, and the information from the previous video on the pumping theorem for context-free languages. So the first thing we're going to cover is what we actually need to do to show that a language is not context-free using the pumping theorem. So what the pumping theorem is a property which is true for every context-free language. So all we need to do when we have a language is show that this property doesn't hold for that language, and then we've immediately proven by contradiction that that language cannot be context-free. So what we need to do is take our language and then prove that this statement here is false. So when we falsify statements with existential and universal quantifiers like this, we end up swapping all of them and then we negate all of the parts. So we need to show that for all k, which is why when we do our proofs we don't pick a particular k, we just use k in the proof so that we can substitute any value we want, that there is a string in the language. So that's why we only need to pick a particular string that works for any k. That for all of the ways of chopping the string into 5 consecutive parts, which is why when we go into the proof later, you'll see that we need to address a number of cases. As long as the string is broken up into those 5 parts, that the v and y part are not both empty, and the vxy part does not contain more than k characters, then we need to finally show that there exists a non-negative q such that the string that we make by pumping in q times or pumping out once is not in the language. So as soon as we've done that, we have proven that that particular language is not context-free, and that's what we're going to go through for one particular language now. So the language that we're going to talk about is very similar to the language that we used as our first example for proving not regular, which was a to the n, b to the n. This is the same language, but then we just say that there needs to follow the same number of c's. Now we can see how intuitively why a push-down automata would struggle to do this, because whilst we could use the stack to count the first lot of a's, in counting the b's that follow, we are going to empty the stack, which then leaves us with nothing to do to end up counting the c's. Now this hand-wavy explanation is not by any means enough to prove that the language is context-free, but it's good to have a little bit of an intuition for these sorts of things, because when you get given a language that you don't know the membership for, you need to make an initial guess before you can move on. So this particular language is not context-free, and we're about to prove it. So as always, the choice for the string can be important, because sometimes you can hamper yourself where you choose a string and it's actually either very difficult or actually impossible to apply the pumping theorem for that particular string. Now, it's not all doom and gloom. In this particular case, the choice that we can use is very simple. Just AK, BK, CK. The reason this works is we have this restriction that VXY must be less than or equal to K. Now, if you remember from the pumping theorem for regular languages, it was always good to choose our string just big enough that our XY part in that case was always in the start bit, which made our pumping very easy. It's similar in this case, because what we do by doing this is we make sure that there is no way that we can have V and Y both in the A's and the C's at the same time, because that would require this part of the string to contain all of the B's and some other characters, and the B's already contain as many characters as VXY can contain by this inequality here. So this is the string that we're going to work with. Larger strings would work too, but something like a to the k on 2, b to the k on 2, c to the k on 2 would be quite difficult to prove. So in a pumping theorem proof for the context-free languages, we often end up in a case where we need to prove a number of cases, and that is because the VXY chunk of the string can move around anywhere. It's not tied to the start like it is for the pumping theorem for regular languages. So what we often do is break our string up into regions, usually regions that have a homogeneous set of characters. So in this case, region 1 is all of the A's, region 2 is all of the B's, and region 3 is all of the C's. Now, the good thing is in this case, these are each K characters long, which means that when we think about our section VXY, which has to be less than or equal to K, there's only so many ways in which we can shove that down into there without violating this inequality here, which we know to be true. So what we have is, the first case, is that V and Y can be sitting both in region 1. So they're short enough and they're both sitting here. So maybe the start of the string U is empty. It doesn't really matter, but in any case, V and Y in the first case are completely contained within region 1. Now there are two very similar cases where V and Y are both fully contained within this. So I'm going to write the X in here as well, just so you remember that there is a potentially non-empty string between V and Y in each of these cases. So that's a set of cases, but if you think about it, we can also have the problem where V and Y are somehow straddling the boundary. So that's what our case 4 is. So that is, V is completely in region 1, so completely made of A's, and Y is completely within region 2, and X is whatever's in between the two of them. And our fifth case is a similar one where the V is completely in region 2 and Y is completely within region 3. So I'd like you to maybe pause this video for a second here and see if you can think of any other cases that can happen subject to the conditions that Vxy is less than K and V and Y are not both empty. Okay, so hopefully one of the cases you came up with is that V or Y could cross a boundary on their own. So we've already covered the cases where V and Y are completely within one boundary but in different regions themselves. But we could also have something where, say, V or Y is something that goes across the boundary between the A's and B's. So there's actually some A's and B's in V or Y, and the same for this boundary here. Now, we have one other case that we don't have to worry about, and that is V or Y being simultaneously in region 1 and 3, and that is because this inequality holds, which means that V and Y can't span that far. We don't have to, for instance, worry about Y being in region 1 and V being in region 2 because V comes before Y. So there are a number of possible ways in which you could imagine popping a V and a Y in there, and none of those actually fit the constraints of the context-free pumping lemma. So these are the cases. So what we need to do is show that for all 6 of these cases, we are able to pump out or pump in and end up with something that is not in the language. So let's talk about the first case. V and Y are both in region 1. This one's pretty simple. If V and Y are completely in region 1, then between the two of them there is a non-empty number of A's. So either of them could be empty, but together they must have at least one A. So all we need to do is pump out, and now we will have a string of the form A to the K minus P, B to the K, C to the K, where P is a a positive integer. And this does not fit the form of the language, and so we've managed to pump out in that case. So it doesn't matter how many A's V and Y have between them. If V and Y are both in the first region, we are able to pump and get a string that is not in the language. Now you'll note that for cases 2 and 3, where V and Y are completely within these regions, the exact same reasoning holds. We pump out, and then we end up with a string that does not have enough either A's or B's or C's to match the other 2 sets of letters, and therefore doesn't fit the language A and B and C. So those cases are actually pretty simple. It's not much more complicated than the reasoning we had to do for the pumping theorem for regular languages. So the next case is where we have V in region 1 and Y in region 2. Now, when we think about the fact that V or Y could either be empty, it doesn't really make sense to consider that case here, because if V is in region 1 but is empty, it's not really in region 1. So we can say that if V or Y are empty, then, and the other one is completely contained within one of the three regions, region 1, 2, or 3, then it really is the previous three cases that we've considered. So in this case, we're considering something that's empty. Something that's not empty in either region 1 and region 2. So what we do again is we can just either pump in or pump out, and now we will have changed the number of A's and B's, and they may be both changing at the same time, but they will not match the number of C's. And so we'll end up with, let's say we've pumped out, we'll end up with A, B and C, where these might be completely two different sizes, because V and Y do not have to be the same size, even though we have to pump them out the same amount of times. But where I and J don't equal K. And therefore, this will not be in the language. The exact same reasoning applies again when we stick V and Y in region 2 and 3 respectively, because we do the same reasoning, it's just whether these, we're talking about A's and B's versus C's, or B's and C's versus A's, it doesn't really change anything. So it's perfectly valid to say that the same reasoning applies in case 5 as it does in case 4. So now we come to the very last case, where V or Y is crossing a boundary. Now, if we've got 4 ways this can happen. Y can be crossing this boundary, in which case V is going to contain some A's. Or V could be crossing this boundary, but if it is crossing this boundary and actually has some A's in it, and this section here is K characters long, then we know that Y can't be going over into the C area. So Y has to be completely contained within region 2. Or we could have Y crossing this boundary here, but V will have to be completely contained within this region here. So I'm just going to draw some dotted lines to sort of show what's happening in these cases here. So we've got certain things splitting the boundary in certain cases. And the last case, we could have V containing both B's and C's, sorry, and Y being contained completely within region 3 somehow. Now, when we pump, 2 things are going to happen, because we can't pump V and Y separately. Any A's or B's that are in the section that is not crossing the boundary will be pumped in or out, and these sections may be empty, but we know that the section that's crossing the boundary is not empty, because otherwise what we really have is one of the previous 5 cases we've already considered. So in this case, we definitely know that the bit that's crossing the boundary here is non-empty. So even though these bits here may be empty and not containing any actual characters, the bits crossing the boundaries will be empty. So we have 2 options. In my opinion, pumping out is the easiest one to consider, because if we pump out when we have something that's crossing this boundary here, we know that we can't have something crossing the opposite boundary here. Which means that if we pump out, we're going to be removing some A's and some B's, but we won't be modifying the number of C's. So the number of A's and B's will each be less than the number of C's, and the string that we end up with won't be in the language. And we can do the exact same thing when we have something crossing this boundary here, because we know it can't simultaneously cross this boundary. So we can pump out, which will remove B's and C's, but the A's will be left untouched, and there will now be more A's in the string than there are B's or C's, and therefore the string will not be a member of AN, BN, CN. The other way to consider it, that often gets mentioned, is we could pump in. Now what happens when I have, for example, A, B, 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 C, 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 and I grab a chunk of this that has an A and two Bs, for instance. That could be one possible case. If I pump that in, what I'm going to get is the original three A's, and then I'm going to get the bit that was already there, so the A and two Bs. And then I'm going to get another copy of the A and two Bs, and then I'm going to get the two Bs and four Cs that I had originally. So these parts here match, these parts here match, and now I have this hodgepodge string in the middle here. Now there's two ways to think about why this isn't in the language. Firstly, there are not an equal number of A's and B's because we've increased the number of A's and B's, A's, B's and C's, because we've increased the number of A's and B's and we haven't modified the number of C's. But the other thing is it no longer matches the form of the string, because remember, every single string in A and B and Cn is also a member of A star, B star, C star. And it's clear that this doesn't fit A star, B star, C star. It's got some A's, followed by a certain number of B's, followed by a certain number of A's again, which is already out of the case, and then some B's and then some C's. So there are two ways to reason. There are several ways to reason in this case. You can talk about how the form of the string has been violated because we've put B's and A's out of order, or you can simply pump out and then reason that in this case we cannot simultaneously be pumping out strings in the other region, and therefore the counting constraints are no longer satisfied. But in either case, you can pump out and the string won't be in the language. So in conclusion, what we've managed to show that for every positive k, and we did this because we reasoned about our string in terms of k without ever setting k to be a value. So we can stick, if our proof worked in terms of some arbitrary k, then it works for all k. And then we've shown that there is a string because we picked one. It was A, K, B, K, C, K. That was in the language. And then we showed that no matter which way we chop it up, and that's why we had to consider 6 different cases, because all those cases were based on ways we could chop it up, such that these constraints were satisfied, which is why we only had to consider 6 cases and not many other cases as well. We showed that there was a value. Now, in every case we ended up pumping out, so the value for all of the cases that we talked about was 0, but we could have picked another Q and if we were able to pump out of the language, then that was valid. But we showed that there was such a Q, such that the string that we got after we pumped in Q times was not in the language L. So we showed that the pumping theorem for context-free languages did not apply to the language that we were talking about, and therefore, by contradiction, we've proven that the language can't possibly be context-free. So what you should have gotten from this video is an idea of how to use the pumping theorem for context-free languages to show that a language is not context-free. There'll be several examples, including probably going over this example again in lectures, but as well as that, you can also look at there are 4 good examples in your textbook, and then we'll also cover some more in the tutorials.